The universe just flashed a light we still cannot explain. From the depths of space, without warning, come bursts of radio energy so powerful they outshine entire galaxies, yet they vanish in less than the blink of an eye. These are fast radio bursts, and they are one of the greatest mysteries in modern astronomy. By the end of this journey, you will understand the frantic scientific chase to decode these signals and why they might hold the key to mapping the invisible fabric of the cosmos. What cosmic object can unleash such staggering energy in a mere millisecond? And what do these random flashes tell us about the most extreme environments in existence? The story begins with a single, baffling signal that nobody believed could be real. What would you do if you found something that broke all the rules? It was hidden in old data, a ghost in the machine. In 2007, astronomer Duncan Lorimer and his student David Narkevic were not looking for cosmic explosions. They were engaged in the meticulous, patient work of sifting through years of recordings from the Parkes radio telescope in Australia, hunting for the steady, rhythmic pulses of distant neutron stars. But within that mountain of information, they found something that did not tick. It shrieked. A single spike of radio energy, unimaginably intense, was captured in a recording from 2001. It lasted just 0.005 of a second, a burst so brief you would miss it if you blinked, yet its signal was stretched and dispersed in a way that screamed it had traveled across an immense, intergalactic void. This was the Lorimer Burst, and it broke the mold. Nothing in our cosmic neighborhood, not a flaring star or a colliding asteroid, could produce such a powerful, fleeting signal from so far away. The energy released in that sliver of time rivaled what our sun puts out over many days. When Lorimer and his team published their findings, the reaction from the wider astronomy community was not excitement, but deep skepticism. It had to be a mistake. Perhaps it was terrestrial interference, a passing satellite, or even a glitch from a microwave oven in the telescope's break room. The idea of a millisecond flash from another galaxy, a phenomenon with no known explanation, was so extraordinary that it challenged the very framework of what we thought was possible in the universe. This single anomaly, dismissed by many as noise, became the first clue in a much larger mystery, a faint echo from the dark that demanded an answer. For 7 long years, that first burst stood alone. It was a cosmic one-off, a brilliant flash in the archives with no echo. Astronomers scanned the skies, but the radio silence was profound. Had they truly witnessed a cataclysm in a distant galaxy, a singular event never to be repeated, or was the simpler, more disappointing answer the correct one? That the Lorimer Burst was just a sophisticated glitch, a trick of the data, leaving a handful of scientists chasing a ghost, this period of doubt was crucial. It transformed the burst from a curious anomaly into a hardened mystery. To solve it, researchers knew they had to find another one, but the challenge was immense. Think of it like trying to capture a single, specific lightning strike somewhere on Earth, using a camera that can only look at a tiny patch of sky at a time, and you do not know when or where it will happen. Fast radio bursts are that unpredictable and that brief. Traditional telescopes were not built for this. They were designed to stare intently at known objects, not to constantly swivel across the cosmos, hoping to catch a millisecond flash out of the corner of their eye. The entire search strategy had to be reinvented. Teams began developing new, incredibly sensitive digital backends and sophisticated software pipelines capable of processing torrents of radio data in real time, sifting through the cosmic static for that distinctive, dispersed spike. This technological arms race, born from years of frustrating silence, was quietly setting the stage for a revelation that would change everything. The ghost was about to become a crowd. The breakthrough arrived not from a single pointed search, but from a telescope built to see everything at once. In the mountains of British Columbia, a radical new instrument began scanning the skies in 2017. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, looks nothing like a traditional dish. It is a stationary array of over 1,000 metal cylinders arranged in 4 long, curved troughs, resembling a series of half-pipes pointed at the sky. This design gives it an enormous field of view, over 200 times the area of the full moon. While other telescopes peer through a keyhole, CHIME threw open the curtains. It was not built to find fast radio bursts, but its ability to watch a vast swath of sky every single day made it the perfect all-sky monitor for these fleeting cosmic flashes. It was listening for the universe's whisper, and instead it heard a roar. The data that began streaming in was nothing short of a revolution. Where astronomers had once painstakingly catalogued a few dozen bursts over a decade, CHIME started finding them by the hundreds and then by the thousands. The floodgates had truly opened. Fast radio bursts were not rare, singular cataclysms. They were a constant background crackle in the cosmos, happening all the time, all across the sky. This deluge of data transformed the entire field overnight. The central question was no longer, do these things exist? It became, what are all these different things? Scientists were suddenly handed a vast catalogue of signals, each with its own subtle fingerprint of energy, duration, and dispersion. They could now begin to classify them to see patterns. They discovered that most bursts appear to be one-off events, but a precious few, less than 5%, repeat. These repeating sources became instant celebrities, precious cosmic laboratories that astronomers could revisit, study, and monitor for changes over time. The mystery had multiplied, but for the first time, it had also given researchers enough pieces to start building a real picture. These repeating bursts became the first real keyholes into the phenomenon's heart. To understand what we are seeing through them, we need to dissect the anatomy of a fast radio burst itself. Imagine, for a moment, a single spark, not from a campfire, but from a cosmic forge so powerful that for just a few thousandths of a second, it outshines every star in its entire host galaxy, but only in the radio part of the spectrum. That is the raw, staggering scale of an FRB. All that incomprehensible energy is packed into a blink so fast that if it lasted a full second, it would contain tens of thousands of these bursts back to back. The sheer distance of these events is another cornerstone of their mystery. When astronomers trace the path of a burst back to its source, they often find it originates in a small, faint galaxy billions of light years away. This is not a local event in our Milky Way. It is a message from the universe's deep past, from a time when our planet was barren, traveling across cosmic voids to reach us now. The proof of this incredible journey is etched into the signal itself, in a property called dispersion. As the burst races through space, it does not travel through a perfect vacuum. It traverses a thin soup of charged particles, the ionized gas that floats between galaxies. This cosmic plasma acts like a prism for radio waves. The lower frequency radio waves, think of them as the deeper notes, get slowed down just a tiny bit more than the higher frequency waves, the cosmic treble. By the time the entire burst reaches our telescopes, it is stretched out. The high notes arrive first, followed a fraction of a second later by the low notes. The greater the stretch, the more intergalactic material the signal has passed through, and therefore the farther it has come. This dispersion measure is the celestial odometer reading that confirms these are not local glitches, but travelers from profound distances. So any viable theory must answer a brutal question. What natural engine, likely smaller than a city, can suddenly convert the energy of a billion suns into a focused radio scream, do it in milliseconds, and in some cases, do it over and over again from the same spot? The hunt for that engine would turn toward some of the most extreme and violent neighborhoods in the cosmos. The repeating burst shattered a fundamental assumption. If a single flash could be written off as a cosmic catastrophe, a star meeting a violent end, what do you call a source that screams, goes quiet, and then screams again years later? This critical breakthrough came not from the new wide-field telescopes, but from a legendary giant listening to the sky. In 2016, using the now-retired Arecibo radio telescope in Puerto Rico, a team led by astronomer Laura Spittler made an announcement that sent shockwaves through the field. They had found a source catalogued as FRB 121102 that was doing the impossible. It was repeating. This was not a one-time cataclysm. It was a persistent, temperamental object in a dwarf galaxy 3 billion light-years away, capable of firing off multiple intense radio bursts. That single discovery divided the entire mystery into two distinct paths. It proved that at least some fast radio bursts are not produced by events that destroy their source. You cannot blow up the same star twice. Instead, the repeater pointed toward an engine that could survive its own outburst, a cosmic object with a deep, renewable well of energy that could be tapped over and over. But the behavior of this repeater was as baffling as its existence. It did not tick like a clock. It would fall silent for months, even years, leading astronomers to wonder if it had finally burned out. Then, without warning, it would erupt in a storm of activity, producing dozens of bursts in a single day before going quiet again. This erratic pattern ruled out simple, periodic mechanisms and suggested something far more complex and volatile. The repeater was not just a source, it was a personality, and its unpredictable tantrums forced theorists to completely rethink their models. Any viable explanation now had to account for an object that could lie dormant, accumulate immense power, and then release it in sporadic, millisecond fireworks, all while remaining intact. The hunt for the culprit narrowed to cosmic objects that are both incredibly dense and magnetically ferocious. The repeating bursts gave us a cosmic address, but the map was still impossibly vague. To truly understand what we are dealing with, astronomers needed to do more than just measure a burst's distance. They needed to see its home. They needed to point the most powerful optical telescopes on Earth directly at the spot in the sky where the radio flash came from and take a picture. This is the monumental challenge of localization, and it required a revolution in technique. A single radio dish, even a giant one, gives you a fuzzy blob on the sky, an area that could contain thousands of faint galaxies. It is like hearing a shout in a crowded city, knowing it came from somewhere in a particular neighborhood, but not which building. The solution was to combine the eyes of the world. Using a method called very long baseline interferometry, scientists can link radio telescopes on different continents, from North America to Europe to Australia, into a single Earth-sized virtual instrument. The wider the separation between the dishes, the sharper the resulting image. This global network acts like a cosmic magnifying glass of unbelievable precision. When a bright, fast radio burst flashes, this synchronized array can pinpoint its location in the sky to within a tiny fraction of an arcsecond, an area so small it is like distinguishing two car headlights on the moon from Earth. This precision is the golden ticket. It allows the world's great optical telescopes, like the Gemini Observatory or the Hubble Space Telescope, to immediately swing toward that exact celestial coordinate and capture a deep, detailed image of what is there. The landmark localization of the first repeater, FRB 121102, was a masterclass in this process. The coordinated radio network narrowed its position to a specific speck of sky. The optical follow-up revealed that speck was not empty. It was a small, faint, and turbulent dwarf galaxy over 3 billion light-years away, but the discovery went even deeper. At that precise location, astronomers found not just a host galaxy, but a persistent, steady source of radio emission, a faint hum underlying the brilliant flashes. This was the environmental context theorists had been desperate for. It told them the burst source was not floating alone in intergalactic space, but was embedded in a specific, dynamic neighborhood. Each successful localization since has added another piece to the puzzle, revealing that bursts can come from all types of galaxies, big and small, calm and chaotic. This shift from asking what is making these bursts to asking where they are happening transformed the mystery from pure speculation into a forensic investigation, allowing scientists to finally examine the scene of the crime. For decades, the search had been focused on the universe's far horizon, on signals that had traveled for billions of years. The answer, it turned out, was hiding in our own backyard. In late April of 2020, a known object in our own Milky Way galaxy, a magnetar called SGR 1935+2154, decided to put on a show. Magnetars are a special, terrifying breed of neutron star, the collapsed cores of massive stars that have died in supernova explosions. They are the universe's ultimate magnets, with fields so strong they could strip the information from a credit card from halfway across the moon. This particular magnetar had been restless, emitting occasional bursts of X-rays. But on April 28th, it erupted with a violence that was recorded across the electromagnetic spectrum. Space-based observatories, including NASA's Swift and Fermi telescopes, detected a colossal flare of X-rays and gamma rays from its location. At the exact same moment, two radio telescopes here on Earth, the Canadian Hydrogen Intensity Mapping Experiment and the Survey for Transient Astronomical Radio Emission 2, were pointed in its direction. They recorded something unprecedented. Alongside the titanic X-ray blast came a blisteringly bright millisecond burst of radio waves. This was not just any radio spike. Its intensity, its duration, its very fingerprint was a perfect match for the fast radio bursts we had been collecting from distant galaxies. The only difference was its source. It came not from billions of light-years away, but from about 30,000 light-years within our own galaxy. This was the smoking gun. For the first time, we had witnessed a fast radio burst being born, and we saw its cradle. It was the furious outburst of a magnetar, a star corpse with a magnetic field 1,000 trillion times stronger than Earth's. The connection was undeniable. At least one prolific source of these cosmic flashes had been identified. The theoretical models that pointed to these ultramagnetic neutron stars as prime suspects were suddenly validated by a single, brilliant flash from our own galactic neighborhood. The mystery was not solved, but it had finally found a face. Yet, this definitive answer immediately raised a deeper, more perplexing question. If magnetars are the engines, why do their distant cousins produce bursts millions of times more energetic than the one we saw in our galaxy? That single galactic flash gave the mystery a name, but the true nature of the suspect is even more extreme than the crime. A magnetar is not just a dead star, it is a neutron star pushed to its absolute limit, a cosmic pressure cooker of unimaginable forces. When a massive star, many times heavier than our Sun, exhausts its fuel, it does not fade quietly. Its core collapses under its own immense gravity in a cataclysmic supernova explosion. What remains is a neutron star, an object so dense that a single sugar cube-sized piece of it would weigh as much as a mountain here on Earth. Most neutron stars spin rapidly and have powerful magnetic fields, but a magnetar is a special breed. During that violent birth, if the conditions are just right, the newborn star's magnetic field can be amplified to truly monstrous levels. We are talking about a field a quadrillion times stronger than Earth's. To grasp that scale, if a magnetar were located halfway between Earth and the Moon, its magnetic pull would be strong enough to warp the atoms in your body from over 200,000 miles away. It is a realm where physics becomes unrecognizable, where the very structure of empty space is bent by magnetic force. So how does this magnetic monster create a fast radio burst? Theorists have two compelling and terrifying scenarios. The first involves starquakes. Imagine the Magnetar's solid crust, a lattice of iron nuclei under unimaginable strain from the twisting magnetic field frozen inside. This crust is not perfectly smooth. It can crack like the tectonic plates of Earth, but with consequences far more energetic. When a section of this star crust suddenly shifts, it releases pent-up magnetic energy in a catastrophic tremor. This starquake sends a shockwave rippling through the Magnetar's magnetosphere, the dense cloud of charged particles trapped by its magnetic field. The disturbance accelerates these particles to nearly the speed of light, and as they whip along the curved magnetic field lines, they emit a screaming lighthouse beam of coherent radio waves, a fast radio burst. The second scenario is even more volatile, a magnetic reconnection event. The Magnetar's field lines are not static. They can become twisted and tangled over time, storing immense energy like a coiled spring. When these lines suddenly snap and reconfigure into a simpler pattern, all that stored magnetic energy is released in an instant. It is a short circuit on a cosmic scale, explosively accelerating particles and creating the same brilliant, focused radio flash. Both models paint a picture of a deeply unstable object, where the very fabric of the star itself is a storehouse for apocalyptic energy, waiting for a trigger. Yet for all its explanatory power, the Magnetar model is not a universal key. It beautifully explains the burst from our own galaxy and provides a plausible engine for many distant repeaters, especially those found in young, star-forming galaxies where magnetars would naturally be born. But the universe, in its infinite creativity, seems to have more than one way to make these flashes. Some fast radio bursts are so stupendously energetic that they strain even the Magnetar explanation, requiring almost the total magnetic energy of such a star to be released in one go. Others come from quiet, elderly galaxies where you would not expect to find a young, hyperactive Magnetar, and perhaps most puzzling of all is the exact mechanism. How does the chaotic, explosive release of magnetic energy get funneled into such a clean, coherent radio signal that can travel billions of light years without scattering into noise? That final step, the translation of cosmic violence into a crisp radio chirp, remains one of the most active frontiers in astrophysics. The Magnetar is our prime suspect, caught in the act, but the full story of its methods and its possible accomplices is still being written in the silent language of magnetic fields and millisecond sparks. But a single suspect cannot explain every crime. While magnetars are now the leading theory, especially for repeating bursts, the sheer diversity of fast radio bursts demands a wider investigation. The universe is a laboratory of extremes, and scientists are exploring every corner of it for alternative engines. One compelling contender involves a final, fatal embrace. When two neutron stars spiral inward over millions of years, their last moments are a spectacle of pure violence. In the final milliseconds before they collide and merge into a black hole, their immensely powerful magnetic fields could be whipped into a frenzy, potentially generating a single, catastrophic radio burst. This model elegantly explains the one-off, non-repeating FRBs. It is a cosmic death cry, a unique event that destroys its source, leaving behind only a flash as its signature. Another fascinating idea looks not to collisions but to collapses. Imagine a supermassive neutron star, one so heavy it is right on the precipice of becoming a black hole. For a brief moment, it might be stabilized by its own rapid spin, like water staying in a bucket swung in a circle. But as it loses energy and slows down, that stability vanishes. In an instant, the entire star collapses directly into a black hole. Theorists call this a blitzar, and in that final moment of transformation, the star's magnetic field is severed from its source and snaps outward, releasing its energy as a brilliant, one-time radio flash. Some models even look to more familiar cosmic mechanics. What if a neutron star, wandering through the debris-filled core of its ancient host galaxy, plowed through a dense asteroid belt or a cloud of cometary material? The impact of a mountain-sized asteroid onto the star's solid surface at a fraction of light speed would be a titanic explosion, possibly channeled by the star's magnetic field into a focused radio beam. Each of these models offers a pathway to immense energy, and each could explain certain types of bursts that don't fit the repeating Magnetar pattern. The field remains open to even more exotic possibilities, from the theoretical vibrations of cosmic strings defects in the fabric of spacetime itself, to the highly speculative idea of advanced technology. While that last notion captivates the public imagination, scientists treat it with extreme caution, emphasizing that extraordinary claims require extraordinary evidence, and natural explanations are overwhelmingly more probable. This vibrant theory zoo is not a sign of confusion but of a healthy, dynamic science. It shows that researchers are following the evidence wherever it leads, testing each idea against the growing flood of data. For now, the Magnetar model sits at the head of the table, backed by that crucial galactic detection. But the cosmos has surprised us before, and the final chapter on what creates these brilliant flashes is still being written by the bursts themselves. This scale of power defies easy comprehension. To grasp it, consider our Sun, a nuclear furnace that has sustained life on Earth for billions of years. In just 1 second, it releases enough energy to power human civilization at its current rate for over 500,000 years. Now, imagine compressing all the energy our Sun radiates over an entire day or an entire month into a single, fleeting millisecond. That is the staggering output of a typical fast radio burst. For the very brightest events detected from the deepest reaches of space, that compressed energy could represent decades of the Sun's total output. All of that cosmic fury is focused, not in a broad, explosive fireball, but into a narrow, screaming beam of radio waves. This is the second, even more profound part of the energy problem. The burst is not just powerful, it is coherent. Think of the difference between a hot light bulb and a laser. A light bulb radiates light in all directions, a chaotic jumble of waves that quickly spreads and dims. A laser produces an orderly, marching column of light waves, all in step, which allows its energy to travel vast distances without scattering. A fast radio burst is the cosmic equivalent of a laser, but for radio waves. Its emission is coherent, which is why this pinpoint flash from billions of light years away can outshine the combined radio noise of every star in its host galaxy. This requirement of coherence is what truly pushes astrophysics to its limits. Whatever creates these bursts must not only tap into an almost unimaginable reservoir of energy, it must release that energy in an exceptionally organized, focused way. It is the difference between the chaotic roar of a collapsing building and the precise, piercing note of a whistle. The cosmic engine must be both a powerhouse and a precision instrument. This dual demand forces theorists to envision processes of breathtaking violence and efficiency, where magnetic fields act like cosmic lenses, funneling chaos into a clean, detectable signal. The very existence of these bursts tells us that in the most extreme neighborhoods of the universe, matter and energy can interact in ways we are only beginning to dream of. The true power of these flashes may lie not in what they are, but in what they pass through. Every fast radio burst is more than a message from a distant engine. It is a forensic record of its epic journey across the cosmos. As that coherent beam of radio waves races toward us for billions of years, it does not travel through empty space. It traverses the thin, ghostly plasma that fills the vast voids between galaxies, the scattered atoms left over from the Big Bang. This material is so diffuse that a cubic meter of it might contain only a single particle, making it utterly dark and invisible to our telescopes. Yet, as we learned, this plasma leaves its fingerprint on the signal through dispersion, slowing the lower frequencies just a bit more than the higher ones. The amount of that stretch, the dispersion measure, is a direct tally of every free electron the burst encountered along its path. Think of it like driving through fog. You cannot see the individual water droplets, but if you measure how much your headlights are dimmed by the time they reach a distant object, you can calculate the total thickness of the fog you drove through. A fast radio burst does this on a cosmic scale. By pinpointing a burst's host galaxy and knowing its precise distance, astronomers can calculate exactly how much dispersion the intergalactic medium alone should have caused. Any extra dispersion tells them there is more material out there than our best models predicted. This is where the story takes a profound turn. For decades, cosmologists have faced a puzzling accounting problem. When they tally up all the normal matter, the protons and neutrons that make up stars, planets, and us, that they can see in galaxies and gas clouds, a significant portion is missing. This is the famous missing baryon problem. Theory and observations of the early universe tell us how much normal matter should exist, but a large fraction of it has simply been invisible. Where did it go? The leading suspicion is that it is hiding in the very place fast radio bursts are now illuminating, in that warm, hot intergalactic medium, the diffuse filaments of the cosmic web. By collecting bursts from many different distances and directions, scientists can begin to use them as cosmic dipsticks. Each burst gives a single measurement of the total electron content along its unique line of sight. With enough of these precise measurements, astronomers can start to build a three-dimensional map of where this invisible matter is concentrated and how it is distributed through the vast voids. It is a revolutionary new kind of tomography, using the most violent flashes in the universe to X-ray the faintest structures in existence. These mysterious bursts, once just a cosmic curiosity, have become one of our most promising tools for charting the architecture of darkness itself, turning a puzzle into a key for unlocking another. While magnetars illuminate the present, a single, staggering flash forced us to peer back into the universe's youth. In June of 2022, the Australian Square Kilometer Array Pathfinder, a powerful radio telescope network, captured a burst of exceptional clarity. Catalogued as FRB 2022-0610A, this was no ordinary signal. Its stretched-out fingerprint told a story of an epic voyage. By measuring this dispersion and then using the world's largest optical telescope, the Very Large Telescope in Chile, to find its host, astronomers made a monumental discovery. This burst originated in a small group of merging galaxies so far away that their light has been traveling to us for nearly 8 billion years. We see this event as it occurred when the cosmos was only about half its current age. This is not just a distance record, it is a time capsule. Its existence answers a profound question. The conditions necessary to create these colossal flashes were already in place billions of years ago, when the universe was a more chaotic, star-forming place. The host system, a scene of galactic collision and turmoil, fits perfectly with the idea of a magnetar born in the fiery aftermath of a massive star's death. A young, magnetically ferocious neutron star could have easily formed in that energetic nursery, but this ancient flash also raises new puzzles. Was the engine behind it identical to the magnetars we see in our modern galactic neighborhood, or were the bursts of the early universe even more powerful, born from stars that were purer and more massive than any forming today? By finding bursts across cosmic time, astronomers can begin to trace a family history for these extreme objects, linking them directly to the epochs of peak star formation. Each distant flash is a marker, proving that the universe has always known how to write its most violent stories in millisecond radio light. Yet the universe's most chaotic explosions sometimes whisper of an underlying order. Among the thousands of repeating bursts, a few have begun to reveal something astonishing, a subtle rhythm hidden within their random-seeming tantrums. The most famous of these is known as FRB 180916. For years, astronomers monitored this source, cataloging its sporadic outbursts. When they plotted the timestamps of its activity on a calendar, a pattern emerged from the noise. Like clockwork, every 16.35 days, this cosmic object would enter an active window. For roughly 4 days, it could fire off multiple bursts, sometimes several in an hour. Then, as if a switch was flipped, it would fall completely silent for the next 12 days before the cycle began again. This was not a strict metronome. The bursts within the active window were still unpredictable, but the overall envelope of possibility was clearly periodic. It was a profound clue. True randomness does not create a reliable 16-day schedule. This repeating cycle points irresistibly toward an orbital dance, a celestial mechanism that regularly changes the conditions around the burst engine. The leading explanation is as elegant as it is complex. Imagine a Magnetar, that ultramagnetic neutron star, but it is not alone. It is locked in a binary orbit with a massive companion, perhaps a young, bright star blowing out a fierce wind of charged particles. For most of its orbit, the Magnetar is positioned behind this shroud of stellar wind. Any radio bursts it produces are smothered, absorbed by the thick plasma before they can escape into interstellar space. But for a few days in each 16-day cycle, the Magnetar's orbit carries it to a point where our line of sight peaks around the edge of the stellar wind, or through a clearer channel. Suddenly, the bursts can reach us. Then, as the orbit continues, the window closes again, and silence returns for 12 days. This model transforms the burst from a solitary actor's scream into a duet, where the companion star's presence and motion act as a cosmic shutter, periodically allowing the brilliant flash to be seen. Other repeaters have shown hints of different cycles, some as short as a few days, others much longer. Each claimed periodicity adds a new constraint, a new piece of orbital geometry that theorists must account for. If confirmed, these cycles do not overturn the Magnetar model. Instead, they enrich it, adding a crucial layer of environmental storytelling. They tell us that some of these explosive engines are not isolated hermits, but exist in dynamic, interacting systems where their most violent outbursts are choreographed by an unseen partner's gravitational pull. The search for these hidden rhythms continues, a delicate process of listening for cadence in a storm of millisecond static, each detected beat bringing us closer to mapping the complete cosmic stage on which these brilliant flashes are performed. The repeating bursts gave us a clock, but their home holds another, quieter mystery. Alongside the brilliant flashes from sources like FRB 121102, astronomers detected a faint, steady hum of radio waves emanating from the exact same point in space. This is the persistent radio source, a constant glow that remains even when the Magnetar is silent. It is not the burst itself, but a permanent fixture in the neighborhood, a cosmic landmark that may hold the secret to what fuels these spectacular eruptions. Think of it like a volcano. The fast radio burst is the sudden, catastrophic explosion that lights up the sky. This persistent radio source is the smoldering mountain itself, the visible sign of a powerful, ongoing geological process deep below the surface. So what is this mountain? What could produce such a steady, compact radio glow in the heart of a distant dwarf galaxy? The leading theories paint two very different pictures of the environment around the central engine. The first and most popular idea is a pulsar wind nebula. Imagine the Magnetar not as a quiet object, but as a relentless powerhouse, constantly blowing out a gale of ultra-relativistic particles, a stellar wind moving at nearly the speed of light. This wind slams into the slower-moving gas and debris that surrounds the young neutron star, perhaps material left over from the supernova that created it. At that collision front, the particles are shocked and accelerated, causing them to radiate energy across the spectrum, including as the steady radio glow we detect. In this scenario, the persistent source is a kind of cosmic exhaust cloud, a byproduct of the Magnetar's furious daily energy output. It is a signpost of an active, energetic system. The second possibility looks to a more dramatic past. Perhaps the persistent source is the fading remnant of the supernova explosion that gave birth to the Magnetar itself. A supernova remnant is an expanding shell of ejected stellar material, glowing brightly in radio waves as it plows through interstellar space. If the Magnetar is very young, it could still be sitting inside the hot, radio-bright bubble of its own violent birth. This would be a snapshot of cosmic adolescence, a brilliant flash engine nestled in the still glowing embers of the star that died to create it. Distinguishing between these two ideas, a wind nebula or a supernova remnant, is crucial. Each tells a different story about the age of the system, the density of its surroundings, and ultimately where the burst engine finds its fuel. Is the Magnetar feeding off its own relentless wind, or is it interacting with a dense shell of ancient stellar debris? A persistent radio source is more than a curious side note. It is likely the key to the local environment, the reservoir of particles and magnetic fields that the Magnetar taps into or pushes against to create its spectacular, repeating flashes. By studying this faint, steady glow, astronomers are not just looking at the spotlight, they are mapping the entire stage. The brilliance of these flashes can tempt us toward impossible conclusions. One persistent idea suggests fast radio bursts might be breaking the universe's ultimate speed limit, traveling faster than light itself. This is a compelling illusion, but it is not what we are seeing. The truth lies in a subtle yet powerful property of their signal called dispersion, and understanding it transforms the burst from a mystery into a precision instrument. When a burst erupts from its source, it does not emit a single, pure tone. It is a chorus of radio frequencies, from deep, rumbling lows to piercing, whistling highs. All these frequencies are created at the exact same instant, but as this chorus races through the thin plasma between galaxies, it faces a subtle drag. The lower frequency waves, the cosmic bass notes, interact more strongly with the free electrons in that plasma. They get slowed down just a tiny bit compared to their higher frequency siblings. By the time the entire signal completes its billion light-year journey to our telescopes, it arrives not as a single crack, but as a descending chirp. The high notes hit our detectors first, followed a few milliseconds later by the low notes. This delay is the dispersion measure. It is not a sign of faster than light travel. It is a record of the journey itself, a cumulative receipt for every electron the signal brushed past. The greater the delay between the high and low frequencies, the more material the burst has traveled through, and therefore the greater its distance. This is why dispersion is the celestial odometer that first confirmed these were intergalactic travelers. Far from breaking physics, this property is a perfect demonstration of known physics in action, a tool built into the very fabric of the signal. And this tool's precision hints at an even grander future application, because we can time the arrival of these millisecond flashes with incredible accuracy. They act as the most punctual clocks in the cosmos, launched from galaxies billions of years in the past. Some scientists theorize that by comparing the timing of these bursts with signals from other cosmic messengers, like gravitational waves, we could perform an extraordinary test. We could check if the fundamental constants of nature, like the speed of light itself, have remained truly constant across the vast expanse of cosmic time and space. A fast radio burst is more than a brilliant explosion. It is a time-stamped message, and within its stretched-out notes, we might one day find a signature of whether the universe's deepest rules have always been the same. But one flash of radio light, no matter how brilliant, only tells part of the story. To truly understand the eruption, we need to see it in every possible way at once. This is the frontier of multi-messenger astronomy, a global hunt to capture a fast radio burst not just in radio waves, but in optical light, X-rays, gamma rays, and perhaps even with neutrinos or gravitational waves. Each type of signal carries a different piece of the puzzle. Radio waves tell us about the coherent beam and the journey through space. X-rays and gamma rays would reveal the raw, explosive power and the searing heat of the event itself. A coincident neutrino could point directly to the dense nuclear reactions at the heart of the engine. A gravitational wave signal would tell us of massive, churning motions. Catching all these messengers from a single burst would be the ultimate cosmic autopsy, giving us a complete picture of the cataclysm. The challenge is monumental. These bursts last milliseconds and appear without warning anywhere in the sky. To have any hope, the world's telescopes must act as a single, coordinated nervous system. When a radio telescope like the Canadian Hydrogen Intensity Mapping Experiment or the Australian Square Kilometer Array Pathfinder detects a bright burst, its computers perform a split-second analysis. Within seconds, an automated alert shoots out across global networks to observatories on the ground and in space. On mountaintops in Chile and Hawaii, robotic optical telescopes swing toward the coordinates, trying to catch a fading afterglow. In orbit, satellites like NASA's Swift and Neil Gehrels Swift Observatory, which are sensitive to X-rays and gamma rays, pivot their instruments, scanning the same patch of sky. It is a race against time, a frantic effort to catch the echo of an explosion that is already over. For years, these coordinated campaigns turned up empty for bursts from other galaxies. The signals seemed to be radio-only phenomena that changed with the galactic Magnetar. That event in 2020 was a textbook multi-messenger success. The same Magnetar flare was seen in blinding X-rays and gamma rays by space telescopes, and in a perfect fast radio burst by radio dishes on Earth. It was the proof of concept, showing that at least some of these engines are multi-wavelength beasts. The ongoing quest is to achieve that same success for a burst from billions of light-years away. Finding an optical or X-ray counterpart to an extragalactic burst would be a transformative discovery. It would immediately narrow down the possible theories, telling us the temperature, density, and physical scale of the explosion region in a way radio alone never could. Every time an alert goes out and telescopes around the world point in unison, it is an act of collective hope, a bet that this time the universe will show its full hand. The flood of new bursts revealed a fundamental split in the family. As astronomers began to sort through the thousands of signals, a clear pattern emerged, dividing the cosmic zoo into two distinct and potentially different species. On one side, there are the repeaters. These are the temperamental, chatty objects that fire off multiple bursts over months or years, like the famous FRB 121102. They represent less than 5% of all detected events, but they are priceless to scientists because they can be studied, revisited, and monitored. On the other side are the apparent non-repeaters, the vast majority of fast radio bursts. These are brilliant, singular flashes that have never been seen to repeat, despite years of dedicated follow-up observation. This simple split asks a profound question. Are we looking at two different kinds of cosmic engines, or are we just seeing the same engine at different stages of its life, or from different angles? The evidence increasingly suggests these may be two different beasts. Let us start with their personalities. Repeaters tend to be lower energy events on average. Their individual bursts are often less powerful than the most spectacular one-offs, but they make up for it with their persistence. More tellingly, the structure of their bursts can be different. When you zoom in on the millisecond flash of a repeater, you sometimes see complex substructure, like multiple tiny peaks within the main burst. It is as if the engine is sputtering, releasing its energy in a series of rapid fire crackles rather than a single, clean bang. Many one-off bursts, by contrast, appear simpler and smoother in their profile, a single, coherent spike of energy. This hints that the physical mechanism behind the curtain might be different, a rapid series of magnetic snaps versus one colossal rupture. Perhaps the strongest clue comes from where they choose to live. When astronomers successfully trace a repeater back to its host galaxy, they almost always find it in a specific type of neighborhood. Repeaters overwhelmingly come from young, star-forming dwarf galaxies. These are turbulent, gas-rich environments where massive stars are born, live short, violent lives, and die in supernova, leaving behind the kind of young, hyperactive magnetars that could power repeated outbursts. It is the perfect cosmic nursery for a persistent engine. The story for many non-repeaters is less clear, but some have been localized to very different environments, including massive, quiet, elliptical galaxies where star formation ceased long ago. You would not expect to find a young magnetar in such a calm, elderly galaxy. This points toward the possibility that at least some one-off bursts are produced by a completely different cataclysm, like the final merger of two neutron stars or the collapse of an aging star into a black hole, events that are destructive, singular, and could happen in any type of galaxy. So, could all one-offs eventually repeat if we just watch for centuries? It is possible, but seems unlikely given the current data. The most energetic non-repeaters pack such a staggering punch that if they were produced by a magnetar, it would require the star to dump nearly all of its magnetic energy in one go. An object that survives such an event might be left magnetically dead, unable to ever produce another burst. For these, the evidence leans toward a truly catastrophic, single-use event. The split between repeaters and non-repeaters is now a central driving question in the field. Each new localized burst adds another data point to this cosmic classification project. Are we building a taxonomy of two separate families, or simply learning to recognize the different moods and life stages of a single, enigmatic phenomenon? The answer will ultimately tell us if the universe has one favorite way to make these brilliant flashes, or if it keeps multiple, even more exotic recipes in its cosmic cookbook. This journey is not a straight line through empty space. Between the brilliant flash and our waiting telescopes lies a chaotic, invisible landscape that can twist and warp the signal itself. These distortions come from clouds of magnetized plasma, the thin, electrified gas that drifts through the vast expanses between stars and galaxies. To a beam of radio waves, these clouds are not transparent. They are like turbulent panes of glass, each with its own bumps and ripples. When a fast radio burst passes through such a region, something extraordinary can happen. The plasma acts as a natural lens, but one that is dynamic and imperfect. It can briefly focus the radio waves, amplifying the signal and making the burst appear momentarily brighter to our instruments. In the next moment, as the burst passes through a different part of the cloud, the lens can defocus the beam, scattering the energy and causing the signal to fade or twinkle, much like a distant star appears to scintillate in our own atmosphere. This interstellar or intergalactic scintillation is a subtle fingerprint left on the burst, a sign of the turbulent seas it had to cross. In the most extreme cases, the plasma can be so dense and structured that it creates multiple pathways for the radio waves. Imagine a single flash of light hitting a complex, faceted gemstone. The light splits, taking several slightly different routes through the crystal before emerging. In the same way, a single fast radio burst can be split by a plasma lens, creating two or more faint copies of the same signal that arrive at our telescopes a fraction of a second apart. To astronomers, this presents both a challenge and a remarkable opportunity. The challenge is clear. These plasma lenses distort the original signal, making it harder to measure the burst's true brightness and structure. It is like trying to identify a friend's voice while they are speaking through a fan. The core message is there, but it is choppy and altered. Yet within that distortion lies a hidden gift. By carefully analyzing how the signal has been scattered, scientists can reverse engineer the properties of the invisible plasma cloud itself. They can deduce its density, its turbulence, and even its physical size. Each burst that shows signs of scintillation or multiple images becomes a probe, not just of its source, but of the fine-scale fabric of the space it traveled through. We are using the most violent flashes in the cosmos to illuminate the faintest, most delicate structures in the universe, turning a complication into a new kind of cosmic vision. But to map this invisible landscape, we need more than scattered glimpses. We need a flood of light. The next great leap in understanding these bursts will not come from a single brilliant flash, but from a torrent of them, captured by a new generation of telescopes so powerful they will redefine the very scale of our search. Leading this charge is an endeavor of almost mythical ambition, the Square Kilometer Array. When its first phase is completed later this decade, the SKA will not be a single telescope, but a vast, networked organism of antennas spread across 2 continents. In the remote deserts of South Africa, thousands of dish-shaped antennas will listen to mid-frequency radio waves. In Western Australia, a forest of over 130,000 simple dipole antennas, resembling metallic Christmas trees, will tune into lower frequencies. Together, they will form a collective listening surface of, as the name promises, approximately 1 square kilometer. This staggering sensitivity is what changes everything. The SKA will be so sensitive it could detect an airport radar on a planet orbiting a star tens of light years away. For fast radio bursts, this means it will hear whispers from the edge of time itself. It will detect bursts from the universe's first few billion years, from the epoch when galaxies were just assembling and the first stars were dying violent deaths. More than that, it will find them in overwhelming numbers. Current estimates suggest the SKA could discover tens of thousands of fast radio bursts every single day. That is not a catalog, it is a census. With millions of bursts, the science shifts from studying fascinating anomalies to performing rigorous statistical cosmology. We will see the full population. We will finally have enough data to answer the fundamental question: are repeaters and one-offs truly different species? We will discover ultra-rare subclasses, bursts with bizarre properties that currently appear only once in a blue moon, but in an SKA sky will become regular subjects for study. This statistical power will allow scientists to pit theoretical models against each other with brutal precision, eliminating those that cannot match the observed distributions of energy, distance, and repetition. Alongside this colossal facility, other specialized hunters are emerging. Dedicated all-sky monitors, even more nimble than current instruments, are being designed to scan the entire heavens continuously, ensuring not a single bright flash is missed. And looking beyond our atmosphere, proposals for space-based radio telescopes are gaining serious traction. Imagine a radio observatory on the far side of the moon, a location permanently shielded from the radio cacophony of Earth. In that profound silence, it could listen for the faintest echoes from the cosmic dawn with a clarity impossible on our noisy planet. These next-generation tools are not just bigger versions of what we have now. They are a qualitative shift, transforming the hunt from a patient search for needles in a haystack into a systematic analysis of the haystack itself, revealing its every strand, its density, and its origin. The mystery of fast radio bursts is about to be confronted with a tidal wave of data, and within that deluge, we may finally find the patterns that reveal the universe's most explosive secret. A signal this extraordinary inevitably invites an extraordinary question. Could these brilliant flashes be a sign not of cosmic violence, but of cosmic intelligence? The idea is a powerful one, capturing the imagination in a way that collapsing stars cannot. In the history of radio astronomy, there is a famous precedent for this kind of tantalizing mystery, the WOW signal. Detected in 1977 by the Big Ear radio telescope, it was a strong, narrowband radio burst that matched the expected signature of an artificial signal from space. It lasted 72 seconds, was never heard again, and to this day has no confirmed natural explanation. Fast radio bursts, with their immense power, coherence, and apparent randomness, have sparked similar lines of speculation. Could they be interstellar beacons, or perhaps the leakage from unimaginably vast technologies? Scientists involved in the search for extraterrestrial intelligence, or SETI, treat these possibilities with rigorous caution. The golden rule is that extraordinary claims require extraordinary evidence, and the evidence for a natural origin has grown overwhelmingly strong. The detection of a fast radio burst from a known magnetar in our own galaxy was in many ways a decisive moment. It proved that nature possesses a known, physical engine capable of producing these specific signals. When you have a clear, natural explanation that fits the data, invoking intelligence becomes an unnecessary complication. The scientific consensus is firm. Fast radio bursts are almost certainly a stunning natural phenomenon. Yet, this speculation is far from worthless. The very exercise of asking if a signal could be artificial forces researchers to sharpen their tools. Studying fast radio bursts pushes us to define with ever greater precision what truly distinguishes a natural cosmic event from a potential technosignature. What does a naturally coherent signal look like compared to an artificially engineered one? How does natural dispersion differ from something that might be encoded with information? By understanding these brilliant natural flashes down to their quantum details, we are essentially calibrating our cosmic ear. We are learning to separate the roar of the cosmic jungle from a whisper that might one day be a voice. So while the bursts themselves are likely the universe's most powerful natural radio lasers, the questions they raise refine the very search for someone else who might, one day, be trying to get our attention. The race to capture these fleeting cosmic whispers is a battle against time itself, measured in milliseconds. When a fast radio burst arrives at a telescope, it is not a neat, pre-packaged signal. It is a torrent of raw digital data, a blizzard of ones and zeros representing the faint hiss of the entire radio sky. The first and most brutal challenge is processing this avalanche in real time. A sophisticated software pipeline must analyze the incoming data stream, searching for the distinctive, dispersed chirp of a burst, and do so before the data is even permanently written to the observatory's hard drives. This is like trying to spot a single unique snowflake in a blizzard while the snow is still falling, and making a decision about it before it hits the ground. The pipeline must perform a frantic series of tasks almost instantly. It cleans the data of terrestrial interference from satellites and radar. It tests thousands of possible dispersion measures to chirp the signal, and it applies complex algorithms to flag a candidate that matches the expected profile. All of this happens in a heartbeat. If the software hesitates, the moment is lost forever. But identification is only the first step. Once a candidate burst is flagged, the system must immediately calculate its rough position in the sky. A single telescope gives only a fuzzy location, so networks of dishes spread across a continent, like the Australian Square Kilometer Array Pathfinder, work in concert. By comparing the precise nanosecond the signal arrived at each separate dish, a process called interferometry, they can triangulate a much more precise celestial address. This entire chain detection, verification, localization must be completed within seconds. Why such a frantic pace? Because the true prize lies in what happens next. The instant the pipeline confirms a bright, promising burst, it triggers an automated alert that flashes across global astronomical networks. This alert, containing the burst's coordinates and basic properties, is a call to arms for telescopes around the world and in space. Optical telescopes in Chile and Hawaii receive the ping and begin slewing their massive mirrors to the target, hoping to catch a fading optical afterglow. X-ray and gamma-ray satellites in Earth orbit reorient their sensitive instruments, searching for high-energy counterparts. This is the dynamic, time-critical endeavor of multi-messenger astronomy in action. It is a global scientific nervous system, where a flash of data in an Australian desert can set observatories across the planet into motion within moments, all united in the shared hope of capturing a single, millisecond event in every possible wavelength of light. The entire operation is a masterpiece of coordination, where the relentless speed of computers meets the patient watchfulness of telescopes, all chasing an echo that vanishes almost before it is heard. That precise celestial odometer reading, the dispersion measure, holds a secret about the universe's very structure. While it tells us how far a burst has traveled, its true cosmological power is unlocked only when we can compare it to an independent distance measurement for the host galaxy. This is where the promise becomes profound. Astronomers have two key numbers for a well-localized fast radio burst. The first is the dispersion measure, the total tally of electrons along the path. The second is the galaxy's redshift, a direct measurement of how much the universe has stretched since the light and the burst left that galaxy. Redshift gives us a precise, independent cosmic distance. When you know both numbers, you can start to build a model of the average density of the invisible, ionized material filling the space between us and that distant galaxy. A single measurement is just a point, but with hundreds and soon thousands of precisely localized bursts from galaxies at all different distances, you can begin to chart a map. This map reveals how the density of this intergalactic plasma has changed over cosmic time, as the universe expanded and matter clumped into the vast web of filaments and voids. This is not just mapping missing matter, it is using that matter as a probe for something even grander: the rate of the universe's expansion itself. Different models of cosmology, different values for the fundamental constants that describe dark energy and the universe's geometry, predict slightly different amounts of intergalactic material spread across different epochs of cosmic history. A vast statistical sample of fast radio bursts, each acting as a single calibrated measurement, could provide a completely new, independent dataset to measure these key cosmological parameters. It offers a fresh check on values derived from other pillars of cosmology, like the cosmic microwave background or distant supernova. In an era where precise measurements from these different methods show intriguing, slight tensions with one another, a new tool like this is invaluable. Fast radio bursts could become standard candles for the radio age, not because they have a standard brightness, but because their encoded journey provides a standard account of the space they crossed. Each millisecond flash is a message in a bottle, and the bottle itself, the stretched fabric of the cosmos, leaves its signature on the note inside. The discovery of the engine only deepened the mystery. We have identified a likely culprit in the Magnetar, and we have begun to use these flashes to map the cosmos, yet fundamental puzzles remain, each one a doorway to a deeper understanding of the universe's most extreme physics. The first and perhaps most pressing question is the exact emission mechanism. We know a magnetar's monstrous magnetic field provides the energy, but how does that chaotic energy get converted into a clean, coherent radio beam? Is it a catastrophic starquake fracturing the neutron star's crust, or a sudden reconnection of magnetic field lines like a cosmic short circuit? Or is it a more complex interplay of both? Pinpointing this is like trying to understand the inner workings of a bomb by only studying the flash of light it produces from 1,000 miles away. Next, we must ask if magnetars are the only actors on this stage. The diversity of bursts, from faint repeaters to colossal one-offs, suggests we may be looking at a cosmic zoo of progenitors. Are the most energetic single flashes the final merger of two neutron stars, or the collapse of an overly massive neutron star into a black hole? Does the universe have multiple, distinct recipes for creating these millisecond flashes? The answer will tell us if we are studying one fascinating species or an entire family of cosmic catastrophes. Then there is the baffling behavior of the repeaters themselves. What dictates their erratic schedules? Why do they erupt in frenzied storms of activity and then fall silent for months or years? The leading idea involves orbital companions and clumpy stellar winds acting as shutters, but the precise clockwork behind these patterns remains elusive. This silence between outbursts is as telling as the bursts themselves, hinting at long periods of energy accumulation or changes in the environment we cannot yet see. Closely tied to this is the nature of the persistent radio sources, those faint, steady glows that accompany some repeating bursts. Are they the smoldering remnants of the supernova that birthed the Magnetar, or are they a pulsar wind nebula, a cloud of particles blown out by the neutron star's relentless energy? This faint hum is the crime scene's background radiation, and deciphering it will reveal the age, fuel source, and local environment of the central engine. Finally, how does the host galaxy itself shape the source? We see bursts from turbulent dwarf galaxies and from quiet, elderly giants. Does the type of galactic neighborhood determine the kind of burst engine that forms there, or how it behaves over its lifetime? A burst from a young, star-forming galaxy likely points to a young Magnetar, while one from a quiescent galaxy might be the signature of an older, different kind of event. Each of these questions represents a frontier. The initial shock of the discovery has passed, replaced by a more precise, more profound set of challenges. The journey is no longer about finding a single answer, but about mapping the entire landscape of extreme physics, one brilliant, fleeting flash at a time. Behind every brilliant flash is a network of people listening. This is not a solitary quest for a single genius in a lonely observatory, but a sprawling, international collaboration that spans continents and disciplines. It began with Duncan Lorimer and his student David Narkevic sifting through archival data with patient curiosity. Their discovery of that first anomalous burst ignited the field, but it was the collective effort of hundreds that turned a ghost into a science. Teams at institutions like McGill University, the Massachusetts Institute of Technology, and the University of California, Berkeley, designed the sophisticated software pipelines that now sift the cosmic static in real time. The Canadian Hydrogen Intensity Mapping Experiment Collaboration, a diverse group of scientists from across Canada and beyond, built and now operates the telescope that opened the floodgates, transforming curiosity into a torrent of data. When a promising burst is detected, an alert flashes across the globe, and the European Very Long Baseline Interferometry Network springs into action, linking dishes from Sweden to South Africa to pinpoint the source with exquisite precision. This mystery has forged a unique alliance. Radio astronomers, who are experts in signal processing and telescope design, work hand in hand with theoretical astrophysicists modeling the violent deaths of stars. Plasma physicists who study the behavior of superheated matter in laboratories lend their expertise to understand how magnetic fields can snap and reconfigure in deep space. Cosmologists who map the large-scale structure of the universe see in these bursts a new tool to probe the invisible. They are all driven by a shared, fundamental curiosity. What begins as a millisecond blip on a screen in a control room in British Columbia becomes a catalyst for a global conversation, a puzzle that requires every piece of human ingenuity to solve. This human story of late nights, failed hypotheses, and sudden breakthroughs is the quiet engine behind the headlines. It is a reminder that the greatest cosmic mysteries are not solved by telescopes alone, but by the collective wonder of those who point them at the dark. The evidence points toward a universe where magnetic fury writes its signature in radio light. We now stand at a remarkable point in this story, where decades of frantic searching have coalesced into a coherent, if still incomplete, picture. The detection of a fast radio burst from a magnetar in our own galaxy was the definitive proof we needed. It confirmed that these ultramagnetic neutron stars are the confirmed source for at least some, and likely many, of the brilliant flashes we see. They are a cosmic engine caught in the act, a natural phenomenon of almost unimaginable power, yet the plot thickens with every new burst we catalogue. The sheer diversity in their behavior, from erratic repeaters to singular cataclysms, and the wide variety of galaxies they call home, strongly suggests we are not looking at a single, monolithic phenomenon. Instead, we may be witnessing several subclasses of events, all born from the same family of extreme objects but shaped by different circumstances. Perhaps the key variables are the age of the magnetar itself. A newborn magnetar, still embedded in the hot debris of its supernova, might behave very differently from an older, isolated one. The local environment is another powerful factor. Is the magnetar plowing through a dense cloud of gas, or is it orbiting a companion star whose wind acts as a periodic shutter? Its binary status could dictate the very rhythm of its outbursts. What began as a single, baffling anomaly has matured into a focused investigation of extreme magnetic phenomena in the most compact objects in the universe. We may not yet have a grand unified theory that explains every single flash with one elegant equation, but the field has decisively moved from a state of pure confusion to one of structured inquiry. We are no longer asking if these things exist. We are now meticulously classifying how they live, how they erupt, and what their brilliant, fleeting lives can teach us about the most ferocious corners of reality. This journey from a single, doubted signal to a new window on the cosmos is a perfect portrait of how science truly works. It began with an anomaly, a piece of data that stubbornly refused to fit. That initial discovery was met not with celebration, but with healthy skepticism, a necessary gatekeeper that demands extraordinary evidence. That skepticism, in turn, fueled a wave of technological innovation, driving us to build wider, faster, and smarter telescopes capable of catching the universe in the act. The breakthrough arrived not as a single eureka moment, but as a flood of data that transformed a ghost into a population, a mystery into a field of study. And now we are in the vital, ongoing phase of refining our theories, where each new burst adds a constraint, eliminating some ideas and strengthening others. Fast radio bursts are more than just a cosmic puzzle. They are a living lesson in the scientific method itself, unfolding in real time for all of us to witness. Their ultimate resolution promises far more than just cataloging a new type of explosion. It will force us to understand physics in realms we cannot replicate, under magnetic fields so strong they distort the vacuum of space itself. Solving how these engines work will teach us about the final states of matter, about the behavior of energy at its most extreme and focused. It will show us how the universe writes its most violent stories in millisecond radio light. We have followed the trail from curiosity to tool, from question to map. The story is still being written by every new flash that streaks across the sky. What part of this cosmic detective story did you find most compelling? Was it the patient search, the technological triumph, or the mind-bending physics of the magnetar itself? Let us know your thoughts.